Hello everyone, welcome to the AP Physics C Mechanics Semester 1 final review. So this just covers all of Semester 1, which is almost everything in mechanics except for the unit of rotation. And so this is going to be split into two parts. The first one is more of a content review. So I'm going to go through all the topics in each unit, just going to throw a bunch of terms and formulas at you. And then the second part is going to be like an application review or like a question preparation. We're going to go over at least 10 MCQ questions and one full-length FRQ, all from an actual AP exam that was released. And so without further ado, let's get started with this first part of the content review. We're going to be starting with Unit 1, which is Kinematics. And so this one is really fast when it comes to AP Physics, and so I'm also going to go pretty fast. The main thing to know here is your relationships between the variables. So obviously we have time or time interval, which is the delta t version, and then we have position, we have velocity, and we have acceleration. So I'm going to just go through each one. So for time, the delta time is the time interval. For position, the delta x is the displacement. Now that's different from distance because displacement's what's known as a vector quantity. It has both magnitude and direction. Distance does not. And so it doesn't have a direction, just a magnitude. Velocity is going to be the displacement over the time interval. So change in position over change in time. Now this is different from speed, which is distance over time interval. That's also going to be not a vector. It's going to be what's called a scalar. Velocity is a vector and speed is a scalar. So velocity is to speed as displacement is to distance. And finally, we have acceleration, which is the change in velocity over the change in time. So those are the main definitions of these quantities. Now, since AP Physics C is a calculus-based course, I'm also going to show you the calculus definitions because some of them are going to give you equations for velocity, for example, and not just values. So you have to take the derivative or integral to get the other quantities. Velocity is going to be equal to dx dt, so it's the derivative of position with respect to time. You can also write it as the integral of acceleration with respect to time. Now, there's these plus c's and weird things when it comes to integrals, but either one, you're going to have a definite integral, so it gives you specific times as the bounds, or two, it's going to tell you it starts at rest or some initial velocity, so that plus c can be accounted for. You're almost never going to write a plus c on an AP Physics question. You're just not going to do it. And that's more of a calculus thing. All right. Similarly, we have acceleration is equal to dv dt, derivative of velocity with respect to time, and it's also it doesn't really have an integral. That is jerk, but we don't cover that in AP Physics. And finally, you can write delta x, which is just the change in position, right, as the integral of v with respect to time. Now, technically, this is just position because it's the position function, but if it is a definite integral, you're actually going to get the change in position, not just the position. All right, so those are the main quantities you need to know. And then I'm going to show you graphs because you can just translate these calculus relationships into graphs. You have three main graphs: the position time graph, the velocity time graph, and the acceleration time graph. So the position time graph just shows you what the object's position is with respect to time. So let's say that's a quadratic function like this. That can be translated into a velocity time graph, which is just the values of velocity with respect to time, what your velocity is. And so if you have a quadratic position, that means you're going to have a linear velocity. And I'm just making up these values. Who knows where the intercepts are or where the slope is? I'm just showing you that quadratic position means linear velocity, which also means constant acceleration. Now, if you had linear position, I might actually just use a different color for that. If you had linear position, you're going to have constant velocity and you would have zero acceleration. And finally, if you had constant position, you would have zero velocity and therefore zero acceleration. Okay, hopefully that helps a bit. You could also have cubic position, which means quadratic velocity, linear acceleration, and so on. A lot of different things you can do, but just remember this from calculus, the graphical representation of the derivative. Moving on to kinematic equations. So how do all of these quantities relate to each other? We kind of saw that with these calculus relationships, but there are these equations that just put a bunch of variables together. And so if you know one, or if you know most of them, you can solve for the remaining one that you don't know. And so there's three major ones. There's a total of 5 that you could know theoretically, but I would just memorize these 3, and the other 2 basically are never used on the AP Physics exam. So the first one you should know is the final velocity is equal to the initial velocity plus the acceleration times the change in time. The second one is the displacement is equal to the initial velocity times the change in time plus 1/2 times the change in time squared. And then finally we have v final squared is equal to v initial squared plus 2a delta x. So these are the 3 equations that you should memorize. And what that tells us is just how velocity is connected to acceleration and all that, how displacement plays a role. Now, there are versions of these that I'll get into a second for a vertical. This is all x's, which usually indicates horizontal movement, but we didn't get into 2-dimensional kinematics yet. One quick thing before I do get into that is motion due to gravity, which does play a role in 2-dimensional kinematics. Motion due to gravity is just free fall. So objects are, they have a gravitational acceleration pointed downwards. In this case, acceleration is what is negative g. Negative g. G is 9.8 approximately, so negative 9.8 meters per second squared is the unit of acceleration. And this is always going to be your acceleration if you're in free fall, if you're just falling due to gravity. And so in all these equations, you can just replace it with something like a minus g if it's in free fall. And that's going to be a perfectly valid equation. I'm going to leave it as plus a because that's the more general form. And yeah, I think we can move on to 2-dimensional kinematics. So that's basically just applying this into 2 dimensions. Before I do that, I'm going to quickly talk about vectors, because this is where vectors actually play a role. I know I said that like displacement and velocity are vectors before, but now you really do need to know vectors. A vector has magnitude directions usually represented with an arrow. You got something, the most common vector you're going to encounter here is the velocity vector, or the initial velocity vector specifically. So if you're launched at an angle, for example, something like this, that is what's called projectile motion, and that's the main type of 2-dimensional motion we're going to be looking at. This is launched at some angle theta, and so you can use trigonometry. If you consider this to be a right triangle, you know that the horizontal component is going to be vix, which is equal to vi cosine theta. The vertical velocity is going to be viy is equal to vi sine theta. And so you're going to plug in those into those kinematic equations. Instead of just vi, it's going to become vix and viy. You want the specific components in those directions. Great. And then you can, you basically just use these 3 equations over and over again in both dimensions. So first you do like x dimension, the horizontal dimension, then you do the vertical, and you combine them basically. And so there's two main types of projectile motion, shot from the ground at an angle, or shot like from a point above horizontally. And so if it's horizontal, then it's going to be straight across. There is no angle. There's no initial vertical velocity. And I just think it would be easier to solve these kind of problems because there's no initial vertical velocity. Everything's just horizontal velocity. And that's basically it for 2-dimensional motion. Now, there's a lot of like applications you can do with this, just like different quantities quantities you don't know, and but that's basically the theory of it. And we might do some practice on this in the MCQ. All right, so that's it for our first unit, which was kinematics. Now, our second unit is forces. So let's get ready for that. So force is just a push or pull that may or may not cause a change in motion. Its unit is the Newton, for Isaac Newton, obviously. And we have something important here called the net force, or you can represent it with sigma f, just the sum of all the forces. And since force is a vector quantity, it's going to be the vector sum. Now, balanced forces are when all forces cancel each other, while unbalanced forces are all forces do not cancel each other. And yeah, so I'm going to get into this a little bit later when we talk about equilibrium. And before we do that, though, I want to talk about Newton's laws of motion. So this is basically all you need to know about an intro to forces. And Newton, who this is named after, has three main laws of motion that dictate like forces and everything. So the first law of motion is that an object that starts at rest or in a uniform motion continues at rest or in uniform motion in the same direction with the same velocity unless acted on by an unbalanced external force. If it stays in the same direction with the same velocity, that just means that it has no acceleration. And so what this is basically saying is if the net force is 0, that means that the acceleration is equal to 0. All right. Now that seems pretty straightforward if you already know Newton's second law, which is just that the acceleration of an object is directly proportional to the net force, and that constant of proportionality is mass. So F net equals ma. Pretty famous, one of the most famous equations in physics other than E equals mc squared. But yeah, if you know this, then it's pretty easy to come up with the first conclusion that if there is no force, then there is no net acceleration. All right, and then the third one is Newton's third law of motion. Each force causes an equal and opposite reaction force. And so we write as F of A on B is equal to the negative of F of B on A. And I do realize I need the vector symbol in all of these because these are all vector quantities, but you know what I mean. Since they are all vector quantities, it's reasonable to assume they are vectors. So yeah. So those are his three laws of motion. They're going to come up pretty often here and there in these problems. Moving on to some different types of forces. Some common forces. So gravitational force is the first one, which we have already encountered. So that's going to be Fg. It's just the attraction between objects with mass, also known as weight. And so the formula for this is equal to the mass of the object times g, the acceleration due to gravity, which we know is 9.8. We also have something called the apparent gravitational force. And so that's like how you feel your weight is. And so this just includes vertical acceleration. You're usually going to encounter this in elevators, but the general formula for this is equal to m times g plus a, where a is the vertical acceleration. Now, if that is 0, if you're just at rest vertically, or you're moving with a constant velocity, then it's just going to be mg. But if you are accelerating upwards, it's going to be g plus a. It's going to be even more. You're going to feel more weight. If it's downwards acceleration, you're going to feel less weight. It's negative a in this case because the acceleration is negative, so it's going to decrease your apparent weight. And then if it's complete free fall, that's 0 because a would become negative g like we saw before, and so that's just 0. That's the feeling of weightlessness. All right. There's a few more like smaller forces that like you're going to encounter a lot, but not really any formulas for that. For example, the normal force, it's just always perpendicular to the surface. And yeah, it's usually there to cancel out other forces. For example, on a flat plane, it usually cancels out the gravitational force. Not always, but usually. We also got the tension force, which is just the force due to like a string or a rope. And we got the spring force. The spring force is a reaction force due to a spring. And this is like if you compress it, it starts to expand again, or if you expand it, it starts to compress again. And so the formula for this is equal to negative k times delta x. We're going to come back to this a little bit later in energy and then a little bit later in oscillations. And this value k is just called the spring constant. It's a measure of the resistivity of the spring, and it's just based on like the properties of the spring and everything. Moving on, we have the friction force. Now this is pretty important, so I'm going to take a little I'm going to explain it for a while. So this is just like a resistive force due to like contact with the surface, and it's always going to be parallel to the surface and usually opposite in the direction of motion. There's two main types, static friction and kinetic friction. Static friction is when the object is not already in motion, but kinetic friction is when it is in motion and it's trying to slow it down. So static friction is a bit weird because it's not equal to a set value. There's no formula for it. Instead, it's always going to be less than or equal to the coefficient of static friction times Fn. So this just depends on the surface and the object and everything. Fn is the normal force we looked at earlier. But why that less than or equal to? It's because it's equal to whatever other force it's opposing, because it wants to stay in equilibrium. It wants to not move. So it's always going to be equal and opposite to that until that exerted force is greater than this value. Once it is, then it starts to move. And so FFS is just equal to this maximum value. On the other hand, kinetic friction has a pretty nice formula, mu k times Fn. So very similar to that, but this time it's always going to be equal to that because it's already in motion. And so there's really nothing you can do about trying to, stay in equilibrium. All right. And key thing to know here, mu s and mu k are not always going to be the same. In fact, they're not usually the same. You're going to get two different values usually for it. Or I'll just keep that, honestly. Yeah. All right, and then finally, drag force. So this you learn later on, but I'm going to just introduce it now. There's two main types of drag force, fluid resistance and the actual drag force. And the difference between these is usually just going to be the velocity at which you're traveling. If it's low velocity, so you're going to have the fluid resistance. If it's high velocity, so you're going to have the drag force. And that's not like a clear and cut rule. It's just that they have different formulas. So it's either equal to BV or it's equal to CV squared. And so usually it's going to be low velocities for BV and high velocities for CV squared, but not guaranteed. It'll probably tell you when to use what formula. And drag force does not appear that much on the AP exam. One thing to know about drag force, though, is terminal velocity, and that's just the maximum velocity you can attain during free fall. The way you figure it out is set whatever drag force equation you're using equal to the gravitational force, because that's when you stop accelerating downwards. That's the maximum velocity you've attained. And then you solve for V in whichever formula you use. All right. Moving on. Equilibrium. So finally we get back to net force and everything. How would you solve these kinds of problems? With free body diagrams. So a free body diagram is just a diagram that shows all the forces acting on an object as vectors. And so for example, let's say I have the normal force up here and the gravitational force canceling it out. And let's have some friction, let's specifically FFS, and then a tension force pulling it this way. That is a free body diagram. It helps us solve problems because now we can identify what forces are there, what forces are opposing others and going along with others, and we can write what are called equilibrium equations or balanced equations. Just F net on the x-axis should be equal to max. F net on the y-axis is equal to 0 in this case, because Fn and Fg are balanced, Ft and FFS are not balanced, and so that's it depends on the problem, but it's just a general procedure you would do. And then there are a few applications of forces you should know, just like if they're all touching. So let's say we just have a bunch of blocks that are touching each other, then you can count it as one system, similar to if they have a string between them, but there's that extra tension force that you should be able to figure out. And then Atwood's machines are also pretty likely to show up. So you got a pulley, and you got blocks on either side. One goes up, the other goes down. The accelerations are going to be the same, and the tension force is going to be the same for both. That's basically it for forces. That was a pretty long unit, but I tried to compress it as much as I could. And yeah, moving on to UCM. So UCM is a very short unit. It's just uniform circular motion. And that basically means it's going around in a circle. There's one important quantity you should know here, which is period. That's the time taken for one revolution. And the equation for that is 2 pi r over v, simply because 2 pi r is the circumference of the circle it's traveling and v is the velocity. So it's just a simple distance equal to rate times time, just from the basic physics you learn in algebra 2. But yeah, that is your equation for period. Gonna come up not that often, but you should know it. And there is going to be an acceleration here. And the reason why is because when you're going in circular motion, even though it's uniform circular motion, which means speed doesn't change, your velocity does, because your direction's always changing. In fact, when you're at a certain point, your velocity is going to be pointing tangential to the path. And so when you move even slightly, that velocity is going to change direction. And so because of this change in direction, since velocity is a vector quantity, that means there is an acceleration changing the direction of the velocity. Now, what is this acceleration called? That's the centripetal acceleration towards the center. And so the formula for this is just v squared over r. There are some other formulas, but you can always derive it using the equation for period and everything. So yeah, that's v squared over r. Now, whenever there's an acceleration, there's a force. So we're going to have the centripetal force. Now, this isn't an actual force, not like gravitational force or tension force. In fact, it's like um, it's a filler force. So it describes the nature of the force, but not what force is actually acting on it. Nearly any force can be a centripetal force. You can have tension force if it's like a string in a horizontal circle. So if you're just like turning a ball around, that's tension force. Normal force is if you're in like um, on a skateboard park and you're just traveling around the edge. You can have gravitational force like the earth around the sun. You can have friction force like if you're in a vehicle turning on the road. And the equation for this is just mv squared over r, because F equals ma, Newton's second law. Nothing too big there. And that's really all you need to know for circular motion. There are applications like with forces. For example, you're banking on a road. So cars on a road, you should know that. Pendulums, we're going to get to that in oscillations. But yeah, maybe vertical and horizontal circles and everything. But vertical circles aren't strictly uniform circular motion. So I wouldn't worry too much about that. And yeah, that was UCM. Like I said, very short unit. Moving on to the next one, which is work, energy, power. I'm just going to write WEP because, too long. So there are three major topics here: work, energy, and power. I know. Work is just the force applied on an object over a displacement that is in the line of action of the force. What does that mean? So if you have a box like this and you're lifting it upwards with a string at an angle, but it's still moving horizontally because of normal force and gravity and all that, you're gonna have to do something about this, because your distance or your displacement is not on the line of action of your force. And so what you're going to do is find the component of the force that is parallel to the displacement. And you can ignore the perpendicular component, and I'll get to that in a second. But the formula for this is just F times the displacement, but technically speaking, it's F times the displacement times cosine theta, because of this component that you have to find. Now, if you've taken like pre-calc or some advanced math that deals with vectors, since force and displacement are vectors, you can write as force dot product delta x, and that gives you the exact same thing. It's just if you're given the actual vector components, then you would probably use this formula. If you're given an angle between them, then you would use this formula. And one thing to note, the dot product results in a scalar value. Work is scalar, not a vector. But that doesn't mean it doesn't have a sign. It doesn't have a direction, it just has magnitude, but it has a sign. You can have positive, negative, or zero work. Positive work is if the force is generally in the same direction as the displacement. This is positive work because the component of the force is in the same direction as the displacement. Negative work is if it's in the opposite direction. Let's say you're pulling this way, but it's still like, moving this way. Let's say, for example, or friction. Friction's a good example. You're pulling this way, friction's going that way. Friction is doing negative work on the box because it's moving this way. You're overpowering the friction, but friction is still there. Your net force might be forward, but friction is still backwards. So that's negative work. And zero work is if the force is completely perpendicular to the displacement. Gravity, for example. In this case, the gravitational force is completely perpendicular. It doesn't do any work. It's not moving it in either direction. And so that's zero work, which is why I said you can ignore the perpendicular component of the force. And there's two types of forces that we're dealing with when it comes to work. Conservative forces and non-conservative forces. Conservative just means that the work doesn't depend on the path taken, so it's going to be like the gravitational force. Non-conservative means that the work does depend on the path taken, so it's going to be like the friction force, which when you move through it longer, it's going to do more work on you. Okay, and then one final thing, this is the formula if the force is constant, but work can be variable. So you write as the integral of force with respect to position. And so it's just the area under the force displacement graph. Technically, you should have bounds on this because you're almost always going to, but if they give you an equation, you just take the indefinite integral. And remember when I said that F is equal to negative K delta X for the spring force? Well, you can do the work done by the spring. That's going to have its own formula, negative 1/2 Kx squared. And you can see why, because if you just plug an integral of negative K delta X here, you can just easily derive this using calculus. And so, yeah, that's going to be your formula for the work done by a spring. Note that it's negative. We're going to get to that in a second. Our second major topic for this unit is energy. Energy is just the ability to do work, and that's why we talked about work first. energy and work are very related. In fact, they have the same unit, which is called the joule. I'd mentioned that before, but the unit of work is joule, as is the unit of energy. There's two types of energy that you should know: kinetic and potential. Kinetic energy is when you're in motion and you have energy due to that. Your formula for that is K is equal to 1/2 mv squared. And there's something neat called the work energy theorem that says that the net work done on an object is equal to the change in kinetic energy. So net work is equal to change in kinetic energy. The second type is potential energy, which is energy due to some sort of position. And so you can divide this further into gravitational potential energy, UG, which is due to position above the Earth's surface. There's a bit more nuanced explanation of this, but I'll get to that in a later unit, which is gravitation. This is equal to mgh. And then you have elastic potential energy due to springs, US, is equal to 1/2 K delta x squared. Why is this positive and this negative, you may ask? Again, we'll get to that in a second. But yeah, these are the formulas you should probably know. There's conservation of energy. You've probably heard of it before, but basically says that energy cannot be created or destroyed, can only be converted between like kinetic and potential. And so the basic formula for this is K initial plus plus U initial is equal to K final plus U final. This U encompasses both gravitational and elastic potential energy. Now, this is only valid if all the forces are conservative. That means mechanical energy is conserved. If they're not, mechanical energy is not conserved, but total energy technically is. And so you're going to have initial kinetic plus initial potential plus work of the non-conservative forces is equal to final kinetic plus final potential. This work of the non-conservative forces is just whatever change in energy there is. Change in kinetic plus change in potential. And if you have friction on a surface, then yeah, you're going to need to find that work, and that's going to be in your conservation of energy equation. Now, energy diagrams. Pretty important thing. Maybe not too many questions on it, but you should know what it is. So there's a potential energy curve that looks something like this. This is potential energy, this is mechanical energy, and so whatever's between these two has to be the kinetic energy because they add up to be that. Now, there's a relationship between force and potential energy that you should know. The force is equal to the negative derivative of the potential energy. That just means that the force is the negative slope of the tangent line to this energy diagram. And if you take the integral of both sides here, you get that the work is equal to the negative change in potential energy, which explains this right here. Since the work is the negative version of the potential energy, that makes sense due to this fact that work is equal to negative change in potential energy. So yeah, everything in physics has a reason. All right. One more thing about these energy diagrams here. There's three different types of equilibrium you can be at. Neutral, stable, or unstable. Neutral is if you move it slightly, it just moves that amount and doesn't do anything else. That means it's like a horizontal part of the energy diagram. Stable equilibrium is you can move it slightly and then it comes back to its original position. So it's like a well or a hole. And then unstable is if you move it slightly, it continues to move in the direction and doesn't come back. So that's like the peak of a hill. You move it down, it just continues to roll downwards. And then our final topic for this unit is power. It's a very, very small topic, but it's just the work done over time. And so power is equal to the change in work over the change in time. And the unit for this is watts. It's joules over seconds, which is watts. And this is just the average power, but you can also have the instantaneous power, which is just the derivative of work with respect to time, as probably expected. And there's another formula for this is force times velocity, because if you actually solve for this, work is equal to force times displacement. So if force doesn't change over time, it's just force times change in displacement over time, which is force times velocity. Good to know. All right. We're about halfway done, I would say. We have quite a few topics left. Mainly momentum is next. And then after that should just be gravitation and oscillation. So more than halfway done, but these next few topics are a bit more complicated. So let's get into momentum. I'm just calling it momentum, but it has a lot of stuff. It has center of mass, momentum, impulse, collisions. Easier just to call it momentum. So first, center of mass. Center of mass is just the point at which the total mass of the system can be concentrated and still represents the entire system. It still goes the same motion and forces and all that. And so I'm just going to show you how to write the formula for the center of mass for the x coordinate, but you can do it for any of the coordinates and then combine them together. The formula for this, it's the sum of the products of the mass at a certain point times the position of that point over the total mass. So if you have like a number line, for example, and at position 0, you have 2 kilograms. At position 3, you have 4 kilograms. You can easily just add up the product of the mass and the position to get what the center of mass should be. Now that's if you have a system of particles, discrete particles. If you have a continuous object, then I'm sorry, but calculus has to come into play. It's the integral of x dm over the total mass. So you need a function of the function for the position in terms of the mass, and then integrate that and divide by the total mass. It's very complicated, but barely shows up. Hopefully it won't show up on your AP exam, but cannot promise that. So yeah, the center of mass. There are also some formulas for like specific shapes, like for a circle or a sphere, it's going to be exactly the center. For like a rectangular prism against the center. For a semicircular plate, it's going to be like 4r over 3 pi above the center, which, you know, you can use integrals to get that. But, you know, I wouldn't worry about that too much. And what's nice about the center of mass is that the motion of the center of mass will mirror the motion of the entire object or system. And it will only move along the direction with net external force, which is pretty cool. All right, so that's center of mass. Moving on to the next big topic here, momentum. Momentum is just going to be the product of mass and velocity. So it's represented with a p. Don't ask me why there's no p in momentum, but they wanted to do it that way, probably because m is taken for mass. So this is just equal to mass times velocity. Velocity is a vector, mass is a scalar, and so p is going to, or momentum is going to be a vector as well. It doesn't have special unit, it's just kilogram meters per second, because that's literally what the product of these would be. One interesting thing is that the relationship between momentum and force is the force is equal to the derivative of momentum with respect to time. Now, why is that interesting? Because that is actually how Newton wrote his second law. That is literally Newton's second law when he wrote it. Now you can rewrite this to write F equals ma. I would suggest trying that on your own. It's a pretty nice math exercise. But yeah, that's it's too complicated to introduce momentum in the second unit, I would say. So that's why F equals ma is usually written. Now, momentum, like energy, is conserved, but it's actually a bit better than that, because momentum is always going to be conserved if it's an isolated system. And so the momentum of a system is constant. Meaning that if you have, I'll get to collisions later, but in collisions, momentum will always be conserved. Another topic is impulse. Impulse is J. Again, don't ask me why. That's a force applied over a short interval of time. And so it's the same exact units as momentum for a weird coincidence I'll get to in a second. But it's just equal to force times time, which again is a vector quantity. Now, if just like work, if this was a variable force, you would write J is equal to the integral of force with respect to time. Again, you would use bounds, but not necessary if you have an equation. And what's neat is the impulse momentum theorem, which says that impulse is just the change in momentum, and you can figure that out using this equation and this equation, or more specifically, this equation and this equation. Just integrate both sides and you get this impulse momentum theorem. That's pretty cool. Wouldn't you agree? Okay, and then the final major topic for this unit is collisions. So collision is when two or more objects just hit each other and exert strong forces on each other for a relatively short amount of time. So that's where this impulse comes in. You would have big force, short amount of time, medium change in momentum. Momentum is always conserved in collisions. Sure, the momentum of one object might change, but as a system, it doesn't change. There's two types you need to know, elastic and inelastic. In an elastic collision, both momentum and kinetic energy are both conserved. So you can have the equation or more specifically, m1i v1i plus m2i v2i is equal to m1f v2f, m1f v1f plus m2f v2f. Right. So that's one equation. That's always true for collisions. The second one is kinetic energy is conserved. So just ki is equal to kf. Another equation in case you have like two unknowns that you need to find. In an inelastic collision, momentum is conserved, but kinetic energy is not. There's some loss due to like friction or something. And there's this specific type called the perfectly inelastic collision, where objects literally stick together after a collision and share a common velocity as they move forward. And so that's when the maximum amount of kinetic energy is lost. That's it for this unit. Pretty fast unit right there. Our next one we're going to go over is gravitation. Now, this isn't just like F equals mg. It's a lot more nuanced than that, because this is Newton's law of universal gravitation. In other words, Newton came up with this other law that says that the gravitational force anywhere in the universe, not just above Earth's surface, is this capital G, which is a constant, times the product of the masses divided by the distance between them squared. This capital G has a value of 6.67 times 10 to the power of negative 11. And yeah, key points regarding this gravitation: it's always going to be attractive, never repulsive. It is a conservative force, like I said before. And there's something cool called the shell theorem, which basically says if you have a spherical shell, if you're outside the spherical shell, you can just treat the shell as like a point mass. Again, center mass. You find its center mass, and it's a point mass there, which is pretty cool. So you use the distance to the center, not the distance to the surface. And if you're an object inside the spherical shell, then you're actually not going to feel a gravitational force at all, because even if you're like right on this edge right here, the sure, the distance to this side is smaller, but the absolute area of the other side is large enough that it literally cancels out. Sure, it's farther, but larger area, and the math works out. It actually balances out, and you're not going to feel any gravitational force. Now, if you were to plug in the values for Earth in this, you do get mg, where g is 9.8. Now, that's not true everywhere on Earth. There are some variations that you should know. First of all, if you're above Earth's surface by a significant amount, then it's obviously going to be different, because it's more distance, it's weaker. Similarly, if you're inside the Earth, you're at a depth, it's going to be stronger because you're closer to the center of the Earth. Earth is also not spherical. It's bulging out at the equator, so it's going to be weaker at the equator, stronger at the poles, because it's more distance at the equator. And finally, you're not going to be tested on this yet, because there is a variation due to Earth's rotation. But since you didn't learn rotation yet, you're not going to know what that is. But just know that since Earth is rotating, there's a variation in the Earth's shape as well, which causes the variation in the value of g. If you have multiple objects that all attract each other, gravitational force, it's a vector sum, because force is a vector, and so you're going to need to find the vector sum of all the gravitational forces on a singular object. Moving on, you're not going to probably learn about gravitational field, but you are going to be talking about gravitational potential energy, and that's just UG. Now, the change in UG is equal to negative W, as we've discussed before. And this is just the negative integral of force with respect to time, or with respect to position, sorry. And so what the formula for this is UG is equal to negative G M1 M2 over R. Now, notice this negative. That means that at infinite distance, R is infinite, so it's going to be 0 at infinite distance. And as you bring it closer, it's going to decrease, but it's going to become more negative. And so it kind of makes sense. If you're using the equation mgh, like we did a few units ago, then as you bring it closer to the Earth's surface, it is going to decrease, because height decreases. But in this new formula, it's also going to decrease. It's just going to become larger in magnitude as it does, because of the negative sign. So yeah, you should probably know that. It can be very confusing, but you're going to use it again when it comes to electricity in semester 2. And one of the last few topics for this unit is like satellites and escape velocity. So the escape velocity is just the minimum velocity required for an object to escape from a gravitational field. So the escape velocity is equal to square root of 2gm over r. All of these are properties of the planet or whatever you're on. And so your mass doesn't matter. It's just the properties of the planet, and you still need the same velocity to escape it. Now, once you actually do escape it and you're in orbit, then it becomes a bit different. You're going to have something called the orbital velocity, which is equal to square root of just gm over r. Here, r is the total radius or distance from the center of the Earth, not just the radius of the Earth itself. And so the way you get this formula is just from the circular motion, the formula for the centripetal acceleration and everything. You just said the centripetal force equal to gravitational force and solve for velocity. Okay, and then final topic for this unit, not really like gravitation related, but kind of related. It's Kepler's laws. So Newton had 3 laws of motion. Kepler has 3 laws of planetary motion. So, thinking large scale with this. The first one is called the law of orbits. Basically saying planets move in an elliptical orbit with the star located at the focus of the ellipse. So if you have a planet here, it doesn't move in a spheric or a circular orbit. Instead, it's elliptical, and the star it orbits around is one of the foci of the ellipse. The second one is the law of areas. This one's very confusing to explain, but basically, in equal time intervals, your planet is going to sweep out the same areas. That means it moves faster here, but since the distance to the star is less, it's going to look smaller, but since it sweeps out more, or like it sweeps out for a longer distance, same time, longer distance, it's going to be equal to a very thin slice here. So yeah. And the final law is called the law of periods. Basically, an equation for the period of motion of a planetary body. The t squared is equal to 4 pi squared over gma cubed. You can just rewrite this as t squared is equal to kappa a cubed, where kappa is a property of like the solar system or the system in which you're at. And all it just means is that the period squared is proportional to the cube of the semi-major axis. Yeah, A is the semi-major axis. It's kind of like radius, but for ellipses, not just circles. That's it for gravitation. And our final unit is oscillations. So we're nearing the end here, almost done. Hope you stuck around for the entire time, because after oscillations, that's when this video ends, but we'll have a part 2 on like question preparation. Okay, oscillations is basically another way for like simple harmonic motion, which is just periodic motion. Repeats itself after regular intervals of time. Some important stuff you should know. Period, again, you should know period. But this time you should also know frequency, F. The relationship between that is a period is equal to 1 over frequency. Frequency is the number of oscillations in 1 second, and its unit is what's called the hertz. Hz is the abbreviation, but it's hertz. Another thing is the phase angle, which is just the initial angle that you start at, and also the angular frequency, which is the rate of change of your like angular position with respect to time. And so one cool formula for this is that it's equal to 2 pi times the frequency, because instead of how many revolutions in a second, it's how many radians in a second. So yeah, there's that, which also means it's 2 pi over t. And then finally, we have the amplitude, which is just the maximum displacement from the equilibrium position. There's a few formulas you should know. In this case, all of these are going to be sinusoidal, so like sine and cosine formulas. And so your position is going to be an equation rather than a value. So it's going to be a sine omega t plus phi. You know what all these are. A is amplitude, omega is angular frequency, and phi is the phase angle. Now, for velocity, you can just take the derivative of this. You get omega times a times cosine of omega t plus phi. Just derivatives here, and acceleration is going to be equal to negative omega squared of a times sine of omega t plus phi. And if you look closely, this a sine omega t plus 5 is just the x of t equation. This is equal to negative omega squared times x of t. Pretty cool. And then we also got something called the restoring force. So the reason why this acceleration is negative of the position means that when you're a certain position from the equilibrium position, so let's say it's a spring and it's being expanded right now, the force or the acceleration wants to bring it back to the center. So anytime you're beyond the center, it wants to come back to the center. Below the center, it wants to come back to the center. And so the restoring force is just going to be m times this acceleration equation. We also got energy in this. So the kinetic energy equation technically is equal to 1/2 mv squared. And since v is an equation here, you can write like an equation for this. U is us here, and that's equal to, well, technically us if it's springs, but it could also be pendulums. And so there's not really a formula for that, but you can write the total mechanical energy as 1/2 m times omega squared a no matter what. Now in springs, this would be equal to 1/2 k x delta x squared, because that is true whenever kinetic energy is 0. So when it's at the ends, basically, that's when this delta x is its amplitude, the maximum value. And so you can find an equation for k involving the angular frequency, which we will do in a second. But yeah, that's the equation for total energy. So you can find the potential energy at a certain point by just subtracting those. Now, there's a few interesting relationships between these because of the sine, cosine, sine, and all that. And so, for example, if position is a minimum, that means velocity would be a maximum because of that sine, cosine, but that means acceleration would be minimum as well. since acceleration is minimum, the restoring force would also be a minimum because they're just proportionally related. And then we got the energy stuff. So the kinetic energy would be a maximum because it's related to the velocity, and the potential energy would be a minimum because that's just this constant value minus the kinetic energy. So you should know all these dynamics. You should be able to derive them with these equations. So if you know these, you can probably get through those relationships. All right, let's talk about a few specific systems you should know. One is springs. We've talked about that quite a bit already, but let's bring it back. So if you do set 1/2 m omega squared a is equal to 1/2 k delta x squared, here we're talking about the when it's at the end, so that means velocity is 0, and so kinetic energy would be 0, and so these two would be equal to each other. This means it's at the maximum position, so the amplitude, so these two cancel each other off, and the halves cancel each other off, and you get a formula m omega squared is equal to k, or omega is equal to the square root of k over m. So that's one formula you should know. I think something similar to that is written on the equation sheet. But that means you can get corresponding formulas for frequency is 1 over 2 pi times the square root of k over m. And so the period is equal to 2 pi times the square root of m over k. You don't have to memorize all of this, just memorize one. I would suggest memorizing this one because that's the easiest to derive as well. And then once you do that, you can derive the others using this relationship. You can also have springs in series and parallel. It's a bit tricky, but notice that in parallel, if you have springs like this, that both push like a certain object, then your total spring constant is going to be equal to the sum of the two springs that you're using. In series, if you have something like this and they both push the object, it's going to be a different formula. It's going to be 1 over ks is equal to 1 over k1 plus 1 over k2. And you're going to revisit some of these formulas in electricity and magnetism with resistors and all that. And then the final special case we're going to be looking at is pendulums. We're starting with simple pendulums here, and that's just like, it goes back and forth. It's negligible mass. The string is negligible mass and everything. So here is a different formula. We have omega is equal to square root of g over L. So it's similar to k over m, but it's g over L. You should know that. Mass doesn't matter in a pendulum, by the way. Good to know. And you can derive these other identities from that as well. There's nothing like series and parallel for that, but what you could talk about is physical pendulums. I'm not really going to get into that because it's a very small topic. But what I will tell you is that there's a similar equation to simple pendulums. It's just that... So first, what is a physical pendulum? It's just where like the mass is not negligible. You need to take the mass into account. And so you're going to come up with a different formula. For the angular frequency, it's going to be the square root of mass times g times d over L. Where d is like the... Actually, I don't think you're really going to talk about it because it has to do with rotation and moment of inertia and everything. So yeah, just ignore that. Just focus on the simple pendulum right there. And that's actually it for this video because we're done with oscillations. That was our last unit. And so be on a lookout for the next video, which is just like a quick question preparation. So this was the bulk of the content, but be sure to check that out if you do need help with stuff like that. All right. So I'll see you in the next video, and as always, good luck.